All right, welcome. This is Ralston Valley High School Chemistry's AP Chemistry Lecture Series, Chapter 11, Lecture Number 2, in which we'll be examining properties of solutions, in particular, Henry's law and solubility. Let's move forward. So over the course of this lecture, we're going to be talking about the various different factors which affect solubility, both from a qualitative and a quantitative perspective. Beginning from a qualitative perspective, there are three main factors we're going to look at here which are going to determine the extent to which something will dissolve and form a successful solution. Those factors are, number one, the structure of both the solvent and solute molecules, number two, the temperature of the system, and number three, the pressure. Starting off by having a look at the structure, let's consider how we might expect to see some species dissolve well in a certain solvent and some not. In particular, during our first lecture of this chapter, we discussed the idea that it's really the solvent-solute interactions that are going to determine the degree to which solution formation will be successful. In particular, we talked about that like dissolves like rule as being a generic way to understand what solvents tend to dissolve which solutes. And particularly, we understood that it was really the favorability of the intermolecular forces of attraction between the solute and solvent particles that determined how effective a particular solute was at dissolving in a particular solvent. In general, very strong intermolecular forces of attraction between solvent and solute particles tend to lead to more successful solution formation, as the process of mixing together the solvent and the solute is more thermodynamically favorable. To understand this effect, consider the two molecules which we've shown you here. These two organic molecules on the diagram are, on the left side, a molecule of vitamin C, and on the right side, a molecule of vitamin D3. Now, looking first of all at the molecule of vitamin C, you'll notice here the prevalence of a large number of hydroxyl groups around the outside of that molecule, as well as a carbonyl group right there with the carbon double bonded to the oxygen, and then the ether group right over there where the oxygen is present, linking together two carbons. All of these locations are places on this molecule where we expect to see strong intermolecular forces of attraction between solute and solvent particles if we tried to dissolve vitamin C in water. That is to say, we could form hydrogen bonds in a large number of different locations, leading to very, very strong interactions between those two particles and therefore a more likely successful solution formation. In contrast, if we tried to dissolve vitamin C in a large nonpolar solvent, like say gasoline, primarily composed of octane C8H18, because those gasoline molecules are dominated by very, very strong London dispersion forces, and there is no permanent dipole present on the gasoline molecules, that implies we would not expect to see the ability to form hydrogen bonds between solvent and solute particles here, and therefore the molecules of the solute would essentially be more strongly attracted to each other than they would be to the solvent. And likewise, the molecules of the solvent, that is the octane, would also be more attracted to itself, other molecules of octane, than it would be to the solute particles of the vitamin C. And as such, from a thermodynamic perspective, it seems therefore like we would unlikely see a successful solution formation if we tried to dissolve vitamin C in octane. Now, conversely, looking over at vitamin D3, which is on the right-hand side here listed as a fat-soluble vitamin, notice that this molecule as well is very, very similar to octane in that manner, that it's dominated primarily by very, very strong London dispersion forces. We've got a big molecule with lots and lots of electrons, leading to very, very strong instantaneous dipoles. But there's only one hydroxyl group present on this entire molecule at a site where we could expect hydrogen bonds to form to water. So essentially, yet again, we find ourselves in a situation where these molecules of vitamin D3 would be more strongly attracted to each other via the process of London dispersion forces than they would be to water molecules as a solvent due to the poor ability of water to form hydrogen bonds with this molecule of vitamin D3. We'd expect this to be much more likely to dissolve in something like, say, a fat. A fat, much like octane, is essentially a long hydrocarbon chain, again, dominated by London dispersion forces and nonpolar molecule overall. So really fundamentally, we can't say if a substance in particular is soluble or insoluble in and of itself. It's always going to be soluble or insoluble dependent upon the solvent we are trying to dissolve it in. So it's not just the solute itself, but instead the solvent-solute interaction. Primarily, when you're asked this type of question on the AP test, you're looking for things like we saw here in this example, that is, Polarity is going to be a big driving force there. The ability to form ion-dipole interactions might be discussed. Or alternatively, one of the most favorite ones to look at is the ability to form hydrogen bonds. Now, if you've ever seen this idea from a biology perspective, you might have seen some of these vitamins referred to as either hydrophobic or hydrophilic. Hydrophobic meaning has a fear of water, or hydrophilic meaning it loves water. And in general, what we're really talking about there is the ability of those water molecules to form hydrogen bonds to these solutes themselves. Again, water would be able to effectively dissolve vitamin C, and therefore vitamin C would be called a hydrophilic or a water-loving molecule, whereas vitamin D3, that fat-soluble vitamin, would be more likely described as hydrophobic, as the water molecules are not likely to form hydrogen bonds, and therefore successful solution formation is unlikely with water. All right, so that's kind of the discussion of structure. Look to intermolecular forces to explain it. Let's move on to look at some of the other factors on our next slides. All right, so on our next slide here, we're talking about the second factor which is going to affect the solubility of a particular solute, that is the temperature of the system. As a general guideline, the solubility of most solid solutes tends to increase with temperature. However, note that there are exceptions. Have a look on this solubility curve, which we've drawn for you here, that shows the increasing solubility of most of these solutes as temperature increases. But notice in particular, there is one solute here. This is this cerium sulfate solute down here, which seems like it decreases in solubility as temperature increases. And we can start to explain some of the idea about why solubility might be temperature dependent of solid state solutes by considering the process of dissolving from a perspective of Le Chatelier's principle. An endothermic dissolver, like say ammonium chloride, as it dissolves is going to absorb energy from its surroundings. And therefore, an increase in temperature would likely tend to push the equilibrium to the right as it increases the rate of the endothermic process within the system. Now, that being said, this is not going to universally hold true because, as it turns out, solubility is a very, very complicated process that involves not just energy changes of the dissociation process itself, but also a very, very strong entropy component, as the dissolving process of ionic solutes tends to involve the dissociation into multiple different ions. So solubility, from that perspective, is best understood via description of Gibbs free energy, which we'll approach during chapter 16. But just as a general kind of overall overview here, most of these ionic solutes that you see tend to increase in solubility at higher temperatures. Now, this is, as it turns out, very different from what happens with gas phase species. Most gas phase species tend to become less soluble as the temperature of the system increases. And we see that happen in the world around us in a couple of different places. One of which would be important in terms of the ecosystems in oceanic environments. If you think about a place where we have lots and lots of life within an ocean, you might think about, first of all, a coral reef. But a coral reef, where the water is nice and warm, as it turns out, is a little tiny oasis in a gigantic, essentially desert environment in the open ocean in the tropics. And we understand that that must be the case by looking at the water itself. Tropical water is known for being beautiful and crystal clear, where you can see meters and meters and meters down without having your vision obstructed. Contrast that with a place where the water is much colder, like, let's say, off of the coast of New England or the northwestern coast of the United States. In these locations, we find kind of grayish green water or brownish water, and all of those different colors, rather than the crystal clear blue we're accustomed to in the tropics, generally are due to the presence of large amounts of microscopic plankton living in the water. And the reason why we find so much plankton there, as it turns out, is that there's much higher levels of dissolved oxygen in these places where the water is cooler. And that also correlates to supporting a larger aquatic ecosystem. If you think about where the largest fisheries are on the entire planet, they're not near the equator where the temperature of the water is very, very warm, but instead like places off the coast of Canada, off the coast of Alaska, or off the coast of Norway, where the water is very, very cold and therefore has higher levels of dissolved oxygen present, allowing it to again support larger aquatic ecosystems. You can kind of think about the reason why this is the case by considering that for a gas to undissolve, it has to escape out of the liquid phase and into the gas phase. And as that occurs at greater rates when the molecules of gas have higher kinetic energy and are therefore better able to overcome the attractive forces between the gas phase solute molecules and the liquid phase solvent particles, We would therefore expect to see more of the gas phase molecules to have sufficient energy to escape at a higher temperature, and therefore the gases would be less soluble as temperature increases. All right, so there is a quick overview of temperature's effect on solubility. Let's have a look on our next slide about the effect of pressure. All right, in considering the effect of pressure on the solubility of a particular solute in a solution, it should come as no surprise that the phase of matter which is most pressure dependent in terms of its solubility is the gas phase system. As solids and liquids, as we've previously discussed, generally are already compressed states of matter, that implies that increasing the pressure on either a liquid or a solid generally does not change the concentration meaningfully, and as such has minimal effect on rates of reaction. However, we are familiar with the idea that gas phase particles are very, very compressible, and as such can likely change concentrations easily with changes in pressure in a system. So to understand how this is going to work, let's consider a familiar reaction that we've probably discussed before, in which carbon dioxide gas is going to be bubbled into liquid phase water, and as it does so, it forms the species H2CO3, that is carbonic acid. This should be a familiar process. It is essentially the process of carbonation of water. Now, consider for a moment here if we have a cylinder with a movable piston and some carbon dioxide molecules present in the gas phase above a liquid water solution. And if we take that system and push down on it, that is, compress the gas, those carbon dioxide molecules are going to collide with the surface of the water at a much greater rate, therefore increasing the rate at which they interact with water molecules, and therefore increasing the rate of the forward reaction, which is in fact the reaction in which the CO2 dissolves into the water to form that carbonic acid. Now, conversely, if we were to pull backwards on the piston there, then all of a sudden the gas particles will be spread further apart, decreasing the rate at which they collide with the surface of the water. And therefore, by Le Chatelier's principle, we'd expect to see the system see an equilibrium shift to the left in the direction that therefore produces more carbon dioxide molecules. As it turns out, you see this happen in the world around you every single time you take a bottle of carbonated soda and open up the cap. At the bottling plant, the soda is initially pressurized by injecting large quantities of carbon dioxide gas into the bottle, and then it's sealed. But when you unscrew the cap, those gas phase molecules of carbon dioxide escape out into the greater atmosphere, thereby drastically decreasing the rate of our forward reaction in the written equation and causing a steady equilibrium shift towards the left, which again implies, therefore, the system would respond by, as it shifts left, producing more bubbles of CO2. And this observation is exactly why, when we unscrew the cap of a soda bottle, you would expect to see bubbles form within the solution. So, in general, as an overview of this idea, generally increasing the pressure of the gas increases the rate of collision of those gas particles with the surface of the liquid they're dissolving into, and thereby tends to increase the rate of forward reaction, leading to a greater solubility of the gas phase solutes into the liquid solutions. We also see this, in addition to carbon dioxide and the carbonation process, in the process of scuba diving. You may be familiar with the idea that scuba divers are told not to rapidly ascend from the bottom of wherever they happen to be exploring up to the surface, because as they move upwards and the external pressure around them decreases, that would imply, by the conversation we just had, that the gases which are dissolved within their bloodstream would become less soluble as the pressure outside of them decreased. And as such, those little gas bubbles tend to come out of solution in their bloodstream, and that can be very, very problematic, especially in locations in your body where the blood vessels are very, very small. Things like those tiny, tiny capillaries. In those tiny capillaries, as the dissolved gases come out of solution and form bubbles, those bubbles can burst the capillaries, leading to the scuba diver to essentially bleed out into their own body. This is a process we call the bends, and clearly this is something you would want to avoid as a scuba diver. So, long story short, for pressure changes, it's really only going to affect gas phase systems meaningfully in terms of the changing solubilities, and in general, the solubility of a gas phase solute will increase at higher pressures in a system. Let's move on to our last slide, where we'll see this from a quantitative perspective. All right, so on our final slide here for this lecture, we're going to look at the quantitative perspective of the discussion we had on our previous slide about the relationship between the solubility of a dissolving gas phase solute and the pressure of our system. Now, Henry's law is a very straightforward calculation. It tells us that the concentration of a gas phase solute in units of moles per liter is directly dependent upon the pressure, and the proportionality constant that relates those two variables of concentration and pressure is referred to as the Henry's law constant, which is given the abbreviation K in our equations. Now, note here, folks, that what that really tells me is as the pressure goes up, so does the concentration of the dissolved solute in a linear fashion. And the K value, that is the proportionality constant, we can kind of understand as being not only, number one, temperature dependent, because again, as the temperature changes, we're going to change the relative amount of kinetic energy that those gas phase solute particles have to escape out of the dissolved solution into the gas phase, but also dependent upon the species which we are dissolving, as we understand that the interaction between solvent and solute particles to a large extent determines the solubility of a particular species. It should therefore be no surprise that Henry's law constant is also species dependent as well. The units that you'll see on a Henry's law constant are essentially moles per liter atmosphere, which makes logical sense then, because if I multiply the constant, again, in units of moles per liter atmosphere, by a pressure, which is going to be measured here in atmospheres, then you'll see here that those units of atmospheres cancel out, yielding units of moles per liter, which again would be a concentration. So again, a very straightforward calculation. Again, literally all it means is as the pressure of a gas goes up, so does, in fact, the concentration of that dissolved gas within a solution. Easy peasy, direct linear relationship. All right, so that is it for our second lecture here in Chapter 11. We will see you at lecture number 3. Thanks for listening.